So hello everyone, this is chapter 10 of Chemical Structure and Reactivity by me, your favorite lecture host. And just quick update, I reformed my name into Palladium, so that's my name now, and that's my name on the official COD server. And as you can see, we have the official shoutout list and the YouTube shoutout list on the bottom here. Feel free to comment on any of the YouTube videos, or send me a DM on Discord if you want to be added to the shoutout list. And overall, for the people who have helped support these lectures, thank you for all your help and support. So let's get right into this. So, I want to do a quick recap of chapter 9, because this is chapter 10 now. So, last time, we talked about bonding between the elements. Now in this chapter, we kind of will be talking about many of the aspects from the previous chapter, but kind of expanding on them. And some of the concepts that we talked about previously were orbital energy and size mismatch, the molecular orbital picture of various compounds like lithium fluoride, and how a lot of the terminology that we use for multiple compounds is not true. For example, if you've seen my last lecture, in the book, the author stated that lithium fluoride is not truly an ionic compound. We only use that term ionic for oversimplification. Now, a convenient way to classify the bond characteristics of compound is known as the Van Arkel diagram, which utilizes averages and differences in orbital energies in order to characterize a bond. So after that, we looked at how we can use the radius ratio for determining coordination numbers and structural arrangements. And then we looked at some interesting phenomena such as Zintl phases and isoelectronic structures. And we'll go straight into what this chapter will cover. So, this chapter will utilize, of course, our knowledge on molecular orbital theory. And what we will do is we'll take our knowledge of molecular orbital theory and we'll see how we can model various chemical reactions using this. So we'll first go over on the basics how to understand the redistribution of electrons in a chemical reaction. And for our first example, we're going to use the reaction between the hydride ion, H-, and a proton, H+. Now, both these reactants will end up forming diatomic hydrogen gas, which is H2 of course. And then we'll focus on what curly arrow mechanisms are. So, especially if you're reading Clayton right now, curly arrow mechanisms or arrow pushing will be dispersed throughout this entire book, that entire book. You can't really escape it. So then, after that, we will look at these things known as HOMO-LUMO interactions. So, remember, back in our molecular orbital theory chapters, like chapter 4 and chapter 5, I stated that the HOMO of a molecule is its highest occupied molecular orbitals. So, that's the molecular orbital with the highest energy and also is occupied with electrons. And then the LUMO of a molecule is simply the molecular orbital that has the lowest energy and is unoccupied. Lowest unoccupied molecular orbital. Now, these two orbitals will dictate many of the reactions that we'll cover. And just as a reminder, we're doing a bunch of molecular orbital theory today, and in this book, you will never be free from molecular orbital theory. So, here are the overall key points for this chapter. So, first, we need to understand the redistribution of electrons within a chemical reaction, and we need to use that knowledge to understand why bonds are broken and formed. Now, the next point directly supports this first point, that molecular orbital theory can be utilized to understand how these electrons are redistributed in chemical reactions. Then, next, we talk about what curly arrow mechanisms are, and saying that they are a simple way to sum up chemical reactions without too much hassle. And our last point is understanding the various reactions between the highest occupied molecular orbital, HOMO, and the lowest unoccupied molecular orbital, LUMO, is crucial for modeling how these electrons get redistributed in reactions. Our first example will be the reaction between the hydride ion H- and a proton H+ to form diatomic hydrogen gas H2. So, just as a quick reminder, hydrogen gas is a molecule that has nonpolar covalent bond where the electrons are shared equally among these hydrogen atoms. And using contour plots of the orbitals shown in the image below, there's an overall spread in electron density across this new hydrogen molecule. So if we go back to chapter 2, just going back to that chapter, we outlined how we can use contour plots in order to just kind of act as an easy visualization for electron density in these molecular orbitals or atomic orbitals. If you've been in like Science Olympiad before, right? In like middle school, there's this event called Rhodes Color, and basically we use these things known as topographic maps, and these maps would have lines that are equally spaced apart based on distance and elevation from each other. That's the best way I can put it. But generally, the closer together these contour lines are, the higher the electron density is, and the farther away the contour lines are, then the lower the electron density. Let's go on to our first introduction to curly arrows. So, especially in organic chemistry, you need to know how these curly arrow mechanisms would work. So, this tail of the arrow describes the movement of a pair of electrons. So the start of the arrow shows where the pair of electrons originate from, and that tip of the arrow showing where they end up. So in this reaction, there's one pair of electrons on the hydride ion, and using our curly arrow mechanism, we can draw a curly arrow that has its tail at that pair of electrons on the hydride ion, and at the head of the arrow, we'll draw it in between the two hydrogen atoms. And the reason why we do this is it signifies that we are creating a bond between these two hydrogen atoms. So that is a quick introduction to curly arrows. That past example I went over about the hydride ion and proton, that was kind of trivial and super rudimentary. Now, we need to do something better, which is the reaction known as the protonation of water. So in this reaction, we have normal H2O and a proton. This occurs when you dissolve anhydrous acid in water. And in this reaction, H2O plus a proton yields the hydronium ion, which is H3O+. So now this is a better example, and this will give us a much more comprehensive view on how these molecular orbitals can change in nature from water to the hydronium ion. So right here is a large diagram showing how these various molecular orbitals of water get changed by this proton pulling electron density. Because remember, opposite charges attract, right? So the proton, of course, will be pulling on electron density. There's something a bit more interesting in how the molecular orbitals change from water to hydronium. So in normal water, the first two molecular orbitals, denoted as MO1 and MO2, are considered strongly bonding. MO3 is weakly bonding, and MO4 is non-bonding. However, if water changes into hydronium through the donation of a proton, the strongly bonding MO1 and MO2 molecular orbitals now control bonding between 3 hydrogens that are bonded to an oxygen atom instead of just 2 in water. Now, MO3 also gets a bigger upgrade because it is now stronger in characteristic of bonding within the hydronium ion instead of just weakly bonding. And in addition, MO4 receives an upgrade from being non-bonding to weakly bonding instead. So take for example, MO1 and MO2. Initially there are 2 hydrogens that are bonded to oxygen, and with the donation of a proton, we can see that MO1 and MO2 can now control bonding between these three hydrogens attached to an oxygen atom. Here's the simple curly arrow mechanism for forming the hydronium ion. So, using those structures, we'll just draw a curly arrow with its tail on that lone pair of on one lone pair of electrons on the oxygen atom, and the head will be between the oxygen and the proton, signifying, of course, a new bond. So overall, you can see these curly arrow mechanisms are pretty simple, and they should stay simple for the most part. So next, I want to talk about how exactly does charge distribution change. So back in chapter 1, I discussed that idea of what formal charges were. And formal charges arise from a system where you count electrons basically, with a certain number of electrons in both bonding and non-bonding pairs. However, if we look on the actual charges on the atoms in the molecule, which is the hydronium ion, the real charge on the oxygen will be calculated to be around negative 0.44, which is far from positive plus 1, while the formal charges of the three hydrogens are all equal to plus 0.48. So you can see with formal charges that oxygen gets a plus 1 formal charge, but the actual charge is still negative. And then those are two ways that you can represent, how charge distribution changes. But the third way basically states that there's the overall positive charge that is delocalized among this hydronium ion, which is a bit more cumbersome / awkward to deal with. So next I want to go over an introduction to HOMO-LUMO interactions. As the reaction progresses towards completion, from those various reactants to products that are expected, if we look at the MO picture, orbitals that are present will change to some degree. That's given. Like take for example the protonation of water. All molecular orbitals will change to some degree, but there's one interaction that is super important, which is the HOMO-LUMO interaction. So this interaction will be crucial for understanding how reactions occur. So if we're talking about the overall energy changes of the electrons in these orbitals, the HOMO-LUMO interaction will result in a net lowering of electron energy. And because everything wants to get into a lower state of energy, it can be a driving force for many reactions. And therefore, it's important to categorize what kind of orbitals are involved in reactions, like non-bonding, bonding, or anti-bonding. You can see in this image right here, this is taken from the book, it states that the HOMO-LUMO interaction, because, there are two LUMOs and two HOMOs with two reactants, the HOMO-LUMO interaction that's most likely to happen will happen with the HOMO-LUMO gap being the smallest, as you can see right there. So you can see the HOMO-LUMO that are connected with this wavy line will be more likely to interact than HOMO-LUMO that are connected with this dashed line because the energy gap is lower. There are many ways that you should identify the HOMO and the LUMO, and this will draw back from your knowledge of polyatomic molecular orbital theory that was covered back in chapter 5. And especially with the HOMOs and LUMOs of various organic molecules such as like alkyl halides, doubly bonded species, triply bonded species, and the general ordering of the energies of types of molecular orbitals. So here's the order in the energies of molecular orbitals from highest energy to lowest energy. So the highest energy will be sigma antibonding. One step lower will be pi antibonding. Then in the middle, there are non-bonding orbitals that include lone pairs. And then there will be pi bonding orbitals lower than that, and sigma bonding orbitals lower than that. And for a molecule, there can be multiple candidates for both the HOMO and the LUMO. So you can't really eyeball it or go by some kind of loose guidelines, especially for more complex molecules or molecules that just don't fit that criteria of what you're looking for. So there can be multiple candidates. So next I want to go over how orbitals can change in a reaction. So using computer calculations, and much to the dismay of our good friend Kuravax, I can't get into that, we can examine how molecular orbitals are arranged in molecules and how they change during various reactions, including their energy. So there's one change that we want to look at and understand. So one may think that using our molecular orbital view, you can see one orbital will rise in energy and the other orbital will lower in energy, and at some point there will be a crossing in energies. However, take for example this phenomenon where there's no kind of crossing of energies, and each orbital takes the characteristic of the other orbital. So this is caused from these orbitals having the same symmetry, and this can be thought of, kind of analogous to that picture of when I talked about sp mixing back in chapter 4. So what sp mixing basically was is you can create a molecular orbital from the overlap of s orbitals and a molecular orbital from the overlap of p orbitals, and these molecular orbitals are of the sigma bonding and sigma anti-bonding type. Now, those two molecular orbitals formed from the S and P, if possible, they can mix and interact to create two new molecular orbitals. So that's what we mean by sp mixing. The reaction that I want to go over is the reaction between borane, BH3, and the hydride ion, which is H minus. So first, let's go over some terminology, okay? So in high school chemistry, you may have learned that Lewis acids are defined as compounds that can accept electron pairs, while Lewis bases can donate a pair of electrons to a Lewis acid. So this is different from your Arrhenius definition and your Bronsted-Lowry definition, right? Because with the Arrhenius definition, an acid can form hydronium ions in solution, and a base will form hydroxide ions in solution. The Bronsted-Lowry definition goes off of proton acceptor or donator, and in this case, Lewis acids and Lewis bases kind of fit a bit more broad category because we're saying that these Lewis acids and Lewis bases can either accept or donate electron pairs. So borane is actually a Lewis acid because if you look at the Lewis structure, right, BH3, that boron has not reached its octet state yet, meaning it's electron deficient. So it can accept a pair of high energy electrons, such as in a lone pair of a donor atom, which is the hydride ion, and it can form a new bond. And in addition, the simplest example of a Lewis acid is just a proton, H+, for your information. So right here is an example of a Lewis acid and base reaction. So you can see with this Lewis acid, it can accept a pair of electrons, this carbocation known as in organic chemistry. It can accept a pair of electrons from water. And that means that the water is now a Lewis base, and this carbocation is a Lewis acid. The reaction between borane and the hydride ion, accidentally put diborane there, forms the borohydride ion, BH4 minus. And so, the HOMO in this reaction, the highest occupied molecular orbital, is the filled 1s orbital of the hydride ion, even though, the hydride ion's not a molecule. While the LUMO here is the non-bonding orbital of borane, which is actually attacked by the lone pair on the hydride ion, which then forms a bond, right? I accidentally put bonding molecular orbital. And in addition, if we were talking about like hybridization, right? It's fake, but anyways, we could say that the hybridization of the boron atom actually changes from sp2 to sp3 now that it forms 4 sigma bonds. So next I want to go over this curly arrow mechanism. So the curly arrow mechanism for this reaction is also very simple. We just draw a curly arrow that originates from that pair of electrons on the hydride ion to that kind of space in between the hydride ion and borane, indicating a new bond is being formed. Now, while this is not consistent with that delocalized view of bonding that we covered with this book, it's still a useful way to think of how the outcomes can change. And in addition, we can also, with charge distribution, we assign that negative formal charge to the boron atom in the borohydride ion, but actually, the computer calculations show that most of the charges associated with hydrogen atoms in this polyatomic ion, and not the boron atom. What this reaction between borane and hydride ion shows is that there's an angle of attack. And this angle of attack will be super important. Because Look at this example right here. The best angle of attack will form the most overlap between the HOMO and the LUMO of the reactants. But if you take this example right here, example B, you can see that if the hydride ion were to attack by this direction, then we would get both positive and negative overlap. And there's a much better way that we can maximize our positive overlap. So this is why the angle of attack is super important. Just because it dictates, how these reactions can proceed. Especially with reactions like SN2 and SN1, the angle of attack will be important. Now, we'll have new terms introduced. So, we talked about this notion of what a Lewis acid was, which was borane in our example, and a Lewis base, which was the hydride ion. So, we can use two new terms to better describe borane and the hydride ion. So, the hydride ion can be called as a nucleophile because it's negatively charged and is thus attracted to positive charges, while the borane molecule is, by definition, electron deficient. So it will be called an electrophile, which means it's a compound that's attracted to negative charges, such as, the hydride ion. Now, in addition, here's a little side note. In inorganic chemistry, we will call an electron donor that bonds to a metal ion as a ligand. And we're going to cover that in chapter 17, which is, far, far off. Our next reaction will go over the protonation of ethene. Next will be the protonation of ethene. In organic chemistry, you will learn that alkenes, in strong aqueous solutions of acid, they can be hydrated to form alcohols, with the protonation of the alkene, which is ethene in this example, being that first step. So what this reaction does is it forms a new bond between the carbon and a proton, but it does break the pi bond between both carbons in the process. So given that carbon that's not newly bonded with a hydrogen, a positive formal charge. Now, since the proton has no electrons, then the LUMO in this reaction is the unoccupied 1s orbital, while the HOMO is the pi bonding molecular orbital of ethene. So as the proton approaches, electron density from the pi bond will shift towards the proton, which will weaken that double bond between carbons. And in the resulting carbocation, that pi bond is largely lost, and bonding now involves overlap between carbon and hydrogen orbitals instead. So you can think of that proton kind of pulling that electron density away and thus weakening the pi bond between both carbons. And of course, we're going to cover the curly arrow mechanism. So there are two representations that we can go over. So in our first representation, we of course, draw the tail of the curly arrow on that double bond, and we draw it in between that right-hand carbon and the proton, which of course, signifies a new bond. And the second representation puts more of an emphasis on how we're forming that new bond between the right-hand carbon and the hydrogen. During protonation, the LUMO involves, which starts at the proton's vacant 1s orbital and transitions as a vacant 2p orbital on carbon at the end. And the carbon is sp2 hybridized now with the vacant p orbital, that left-hand carbon, which then becomes the LUMO. Our next reaction, in the past reactions, we talked about the donation of electrons into non-bonding LUMOs, but what if they were anti-bonding instead? Now this will mean that if we donate electrons into an anti-bonding LUMO, then that bond in the electrophile will break if the electrons are donated. So one example, which is, covered in Clayton, like at the start, is known as the nucleophilic addition of the carbonyl group, where there's a pair of high energy electrons which is donated to the pi anti-bonding molecular orbital. And what this does is that it breaks the pi bond between that carbon and the oxygen, leaving just a single bond and thus a negative formal charge on the oxygen. So our simplest example here is between methanol and the hydride ion. So right here's the overall reaction. Unfortunately, I couldn't fit it on the past slide. But the hydride ion attacks methanol's pi anti-bonding molecular orbital and thus breaks that pi bond between carbon and oxygen, and forms new bond between the carbon and the hydrogen. So what I need you to know is that the carbonyl bond is polar, which means that the oxygen will be partially negatively charged and the carbon will be partially positively charged, which creates somewhat of an attraction between that sort of positively charged carbon and the hydride ion, thus meaning that there will be an opportunity for this hydride ion to attack the pi antibonding orbital. Next, I want to go over, some angle of attack. So, as the two reactants in this reaction get closer to each other, the orbitals will of course interact, and electrons are donated from the full 1s orbital of the hydride ion to the pi antibonding orbital of the methanol molecule. And we can sum this entire reaction very conveniently with curly arrow mechanisms. You can see we're drawing one arrow, which shows the attack of the pair of electrons, onto that carbon, forming new bond. And we'll draw an arrow, which shows the redistribution of the pi electrons to a lone pair on the oxygen, which of course is a bit more localized view of bonding, but still allows us to conveniently sum up reactions. Now, next I want to go over the angle of attack from the hydride ion. So right here is the highest occupied molecular orbital, and right here is the lowest unoccupied molecular orbital. So the most optimal angle of attack is around 109.5 degrees to the pi antibonding orbital, which will allow for the most overlap. We talked about the donation of electrons from a nucleophile into a pi antibonding orbital, but that sigma bond, which is, of course, that single bond between atoms, will still remain. So if the LUMO is now a sigma antibonding orbital, the donation of electrons will therefore break that bond. So our first reaction will concern the addition of electrons from a nucleophile to the sigma antibonding orbital of a tetrahedral carbon that is bonded to a leaving group. So it's called a leaving group because it will leave and this nucleophile will bond with that tetrahedral carbon. This is known as the SN2 mechanism. In this image that I showed in the last slide, there will be three changes. So a new bond is now formed between the nucleophile and the tetrahedral carbon. The leaving group X is ejected as the CX bond is broken from the addition of electrons into that sigma antibonding orbital, and the geometry of the central carbon kind of gets turned inside out, like an umbrella. Now, the exact reactants that we'll use for modeling the SN2 reaction is the reaction between H- and CH3Cl. And as per chapter 5, the LUMO of the CH3Cl molecule is the bond between the carbon and the chlorine. That hydride ion will attack the sigma antibonding orbital, backside attack, and it will donate electrons in sigma antibonding, breaking that bond, and thus leaving, chlorine on its own as the chloride ion. And in addition, the pi bonding molecular orbital now shows overlap between that new hydrogen and the carbon, instead of the carbon and the chlorine atom. On the top here is the curly arrow mechanism. So our first arrow will denote that there's a redistribution of electrons forming a new bond between the hydride ion, which is now hydrogen atom, and the tetrahedral carbon. And what we'll do is we'll draw a second arrow that denotes the moving of electrons from the single bond into a lone pair onto this new chloride anion. And in addition, here's a visual representation of the angle of attack. So you can see, especially in organic chemistry, why they call it backside attack. You have to kind of attack that carbon from the back if you want to get the most positive overlap, and thus have the reaction proceed. So that's just the curly arrow mechanism and why the angle of attack is useful. So here's the overall summary of HOMO-LUMO interactions. So electrons are rearranged in a reaction, and using the molecular orbital view can help us to visualize and rationalize why these electrons are rearranged. And one of the highest energy valence electrons are involved, and finding out the lowering of energy of these electrons will act as a driving force for the reaction. And then we talk about how, homo-LUMO interactions are important, and how new bonds are formed when electrons are donated to either bonding or non-bonding orbitals, while these bonds are broken if electrons are donated to anti-bonding orbitals. And then we talked about how curly arrow mechanisms are a clever way to sum up reactions. But don't forget angle of attack. Go over the role of protonation in reactions. So especially in organic reactions, protonation will serve as a way, or these acids can serve as a catalyst for these reactions to happen. So take for example the hydrolysis of ethyl acetate into ethanol, which is faster if this initial CO bond is now protonated. So one reason why protonation is important is because there is now a greater electrostatic interaction increase between that oxygen and the carbonyl carbon. And the second reason is that the LUMO in which the water molecule donates electrons to, which is that, pi antibonding orbital, is now lower in energy. And a lower energy LUMO will allow for a reaction to happen quicker. So now I want to talk about, the exact mechanisms for lowering that pi antibonding energy. So, protonating the oxygen in the carbonyl group will increase its effective nuclear charge, which then means that the energy of the 2p orbital is now lower, meaning that the pi antibonding orbital will also have its energy lowered. And in addition, here's a little fun fact: coordination of the oxygen with the Lewis acid, such as Li plus ion, the lithium cation, also presents similar effects to protonation, lowering the energy of that pi antibonding orbital. So there are many ways that we can represent the protonated carbonyl. So utilizing resonance structures, we can also represent the carbonyl group with the authors of this wonderful book, taking our simple example of methanol. So you can see in this top right image, there are two ways that we can represent methanol. So one way is we have that double bond between carbon and oxygen, and the second way is we don't have any double bonds, just single bonds. And the carbon now has a positive charge, and the oxygen now has a negative charge. And if we go back to chapter 1, I said that if we have multiple resonance structures, then a molecule just doesn't flip-flop between them. No, if we have multiple resonance structures, then the molecule, like true electronic structure, or just like the true way that electrons are distributed, will be somewhat of a mix of all these resonance structures. So this protonation, if we have protonated methanol, it will shift electron density even more towards oxygen, meaning the resonance structure with a full positive charge on carbon and lone pairs on oxygen, aka this one, will contribute more significantly than in this neutral case, which reflects a more polarized pi bond. The intramolecular reactions are reactions that just happen inside one molecule. So in every single previous reaction, we looked at how the HOMO of one reactant can react with the LUMO of another reactant. Now, one example can be that the lone pair on the nitrogen atom in methylamine, CH3NH2, and the carbon-chlorine sigma antibonding orbital in chloroethane can interact with each other to eject that chlorine from the chloroethane molecule. However, when we have both the NH2 and the Cl attached to the same carbon, we can get an intramolecular reaction. So this will happen all in one molecule, and the lone pair on nitrogen will attack that sigma antibonding orbital of the C of the carbon-chlorine bond. So the molecule will not always fall apart, and instead the bond can just be weakened and thus become longer in some situations. So in this image, we can see that the lone pair on this oxygen atom can interact with this kind of carbon-chlorine sigma antibonding molecular orbital to kind of weaken it. So it shows that the carbon-chlorine bond is actually somewhat longer than typical values, as expected. So that's enough about intramolecular reactions. Now we want to go over rearrangement reactions. For some reactions, it's not always appropriate to think about homo-LUMO interactions between two species. So this is known as a pericyclic reaction, And all the bonds that are either broken or formed will lie within one ring. And in such a reaction, the pi bonds are rearranged in the ring, and we can yield a new sigma bond between carbons, which can be explained by the rotation of bonds. And just to show you what I mean by the rotation of bonds, right here are changes in pi orbital arrangement. So we have MOC, MOB, and MOA, which are just various molecular orbitals that are on this molecule known as cis-135 hexatriene. And these kind of should remind you of pi conjugated systems. So with the heat or UV light, the p orbitals can rotate, which allows for a reshifting of pi bonds and forming of new sigma bonds. And in addition, here are the energy plots, as the reactants go from reactants to products. And you can see how there is a lowering of energy, and especially how molecular orbitals C and molecular orbital change. There's no crossing in energy, and that's because they have the same symmetry. So right here is the curly arrow mechanism, which will be always easy to write out. You can see it's just a simple redistribution of bonding pairs. And in addition, since the reaction is symmetrical, we can draw these arrows in either a symmetric or anti-symmetric direction. And just as a reminder, while these curly arrows are somewhat misleading, they are still a useful tool if you want to sum up reactions into a simple diagram. So that's it for the chapter. So our next chapter will focus on the concepts that we've just learned about, and we'll learn about organic chemistry. So this chapter will cover stuff like SN1, SN2, how we can use reducing agents on the carbonyl group, hydrates, hemiacetyls, acetyls, enamines, and just so much more.